Let's talk about this problem. We are given two sorted arrays. Our task is to print intersection or common elements of both the arrays. Both the arrays might contain duplicates, and if there is an element, for example 10 here, it appears 3 times here and 2 times here, but we should be printing it only once in the output. So for this example array, our output is going to be 3 and then 10, right? Even if it appears multiple times in both the arrays, we are going to print it only once. Then 15 is also common, so our output is going to be 15 also. Let's see this example. Here we have double 1, triple 3, then 4 ones, 3, 5, 7. Our output is going to be 1, 3, and 5, 7 are not common, so we are not going to print 5, 7. We are going to print only common elements. And if you are given two arrays which do not have any common elements, then your output is going to be empty. Now please pause this video and try to think of a solution that takes two arrays as input and prints common elements. Let us first talk about a naive solution to solve the problem. The idea of this naive solution is super simple. We traverse through every element of array A. We look for it in array B. If we find it in array B, then we print that common element and we continue for the next elements. The only things left here are how do we handle duplicates. Let's take a closer look at this implementation of the naive idea. I am taking two arrays as parameters. M is the size of array A, N is the size of array B. So we traverse through array A. For every element AI, right, we first check if it is same as previous element or not. So we are comparing with AI minus 1. This is done to avoid printing duplicates. So if you are traversing through this array, when you come to this 20, right, you have already processed this 20 and it was there in this second array, you must have printed it. So you don't want to print it again. That's why we have this condition. And since we are accessing negative index, we need to ensure, since we are accessing I minus 1, we need to ensure I is greater than 0, right? Otherwise, if you access this for I equal to 0, you will be having problems, right? Now, once after checking for this thing, we look for AI in array B. As soon as we find it in array B, we print it and we break the loop, right? Again to avoid duplicates, right? Because this for example is present at multiple places. We want to print only one occurrence. So this is the idea, and time complexity of the solution is clearly upper bounded by n into m, right? You are running a loop m times here, big O of m times here, and big O of n times this loop is running here. In fact, the outer loop is running theta m time and inner loop is running big O of n time, right? It's always run n times and this might not run n times every time, right? So that's why we have used big O notation. Theta of m into big O of n is big O of n into m, or big O of m into n. Here is dry run of this naive approach. When you run for I equal to 0, which means you are looking for element 1, you search for it in array B, you don't find it, you go for 0, 1, 2, 3, this loop runs for 0, 1, 2, 3, you don't find it. Then you run for 1, you search for it in array B, you find it at index 1, so you print it here and you break the loop. Then you run for 2, right, and when you run for 2, you go into this if condition and you skip this element. We are using continuous syntax. When you come to 40, you don't find it, you run for 0, 1, 2, 3. When you come to 60, you don't find it, you run for 0, 1, 2, 3. Now please pause this video and try to think of a solution that works in time complexity better than this. Let us now talk about idea for the efficient solution. We are going to use the idea of merge function of merge sort. We are going to initialize I and j as zeros, then we are going to compare ai with bj, right? And merge function is also theta m plus n, and we are going to solve it in the same time. And since we only need to print the output here, we don't need auxiliary space also. It's going to be simpler than merge function. So we traverse through array A, right? Simultaneously we traverse through array B and we compare AI with BJ. And there are three cases that would arise, right? AI is smaller than BJ, AI is greater than BJ, and AI and BJ are same. Let's understand three cases in this example. We compare 2 and 10 first. I is 0 and j is 0 initially. I is smaller. So what we do in merge sort, we go ahead because this element cannot match with any of the upcoming elements. It's smaller than the first element itself and both the arrays are sorted. Please note that this implementation or this solution is actually using the fact that both the arrays are sorted. The previous solution that we wrote, it would work for any type of array, sorted or unsorted. Here we are actually using the fact. So if 2 is smaller, we move ahead in this array. We compare 20 and 10 now. Now 10 is smaller, so we'll move ahead in this array. Now 20, 20, they are same, so we'll print it. Now how do we handle the duplicates? We can use the same idea as we discussed in the naive solution. If ai is same as ai minus 1 and I is greater than 0, then we'll simply do I plus plus. That's the condition we'll put at the top, right? So this is the condition we'll put at the top before putting any condition. If I is greater than 0, right, and ai is equal to ai minus 1, then what are we going to do? We are going to do I plus plus, right, and we are going to continue the loop. We don't need to check for other things, because if this element was present in array B, this must have been processed already. Now after doing this check and then these three checks, we will be able to print all the intersection elements or common elements. Now please pause this video and try to fill the conditions here and try to write down the complete code yourself. So here are the things we will write in these conditions. If ai is smaller, we'll do I plus plus. If bj is smaller, then we'll do j plus plus. If they are same, then we'll print ai or bj. They are same, you can print any of them, and we'll do I plus plus and j plus plus. Now please pause this video and write the complete code yourself. Here is implementation of the efficient approach. We have I and j initialized as 0. We are running a merge type of loop, I is smaller than m and j is smaller than n. Inside this loop, we have the same condition as the naive solution. If I is greater than 0 and array I is I minus 1, if it is same as the previous element, we do I plus plus and continue. And these three conditions I just discussed. If ai is smaller, do I plus plus. If bj is smaller, do j plus plus. If they are same, then print the current element. In Java, you can use system.out.print and increment both I and j. So let's take a look at this example and let's see the try run. Initially I and j both are 0, right? Now we compare 10 and 2. 2 is smaller, so we do j plus plus. We get inside this loop, right, and we make j equal to 1. Now when j becomes 1, we compare 10 and 20, and this time 10 is smaller, so we do I plus plus and we make I equal to 1. Now I is 1 and j is 1. In the third iteration, we'll enter inside this if condition, right? Because both are same, ai and aj are same, so we'll print 20 on the screen and we'll increment both. So I and j, they both now become 2, right? But this condition will save us from printing duplicates. In the iteration when I and j both are 2, what will happen? We'll enter inside this if condition. And what this condition will do, it will make I equal to next element, which is next index, which is 3, right? Now I becomes 3, so we are going to compare 40 and 20, right, in the next iteration. And 20 is smaller, so we'll make j equal to 3. Now we'll compare again 20 and 40, this 20 this time, and 20 is smaller, so we'll make j equal to 4. And what happens now? J crosses the size, right? J crosses the maximum index. J now actually becomes the size. So we come out of the while loop. If any of them become equal to the size, we need to come out of the loop, and we have printed 20 on the screen. So this is how the solution, this efficient solution works.